Here's the solution for the day 4 bell work. This is an application of the linear programming skill from yesterday's bell work. This problem is about Best Buy selling two different models of phones, a cheaper phone that costs $250 per unit and a more expensive phone that's $400 per unit. We need to read this paragraph and find the objective of the situation. The objective is to maximize the profit. So we need to algebraically model maximizing the profit. This is called the objective quantity. I'm going to select the variable P to mean profit and then write an algebra equation that represents the profit. We're told that the cheaper phone yields a profit of $45 per unit sold. I could model that as 45 times X, where the letter X is the number of the cheaper phone. And then plus, and we're told that the more expensive phone is a profit of $50. So that could be modeled as 50 times Y, where the letter Y is representing the number of that more expensive phone that is sold. There's our objective quantity. To maximize that, we need to graph a shaded-in region of space, locate the vertices, and then use those X and Y values into this expression to see what is the maximum number that this will output. Our next step is to create the constraints. The constraints are inequality statements. So one constraint is that X must be greater than or equal to 0. Because X was representing the number of the cheaper phone, and you can't have a negative amount of phones. Similarly, Y must be greater than or equal to 0. Another constraint involves this information here along with this information here. Best Buy is not willing to pay more than $70,000 on phones. So we can write $250 times the number of that cheaper model plus $400 times the number of the more expensive model must remain less than or equal to $70,000. There's a fourth constraint, and it comes from this piece of information right here. Best Buy doesn't want to have more than 250 phones in stock, and so the number of the cheaper phones plus the number of the more expensive phones needs to stay less than or equal to 250 units. These four inequalities can be graphed to create a closed-in region of space, and then we can find the vertices of that region. So right down here, let's make a graph. Here's quadrant 1 of the X and Y axis system. The first and second constraints create lines right along the y-axis and the x-axis. We need to pay more attention to these two, though, which are diagonal lines. So let's work with this third blue one first. This is in standard form, and I'm going to leave it in standard form and use intercepts method. I'm going to replace y with 0 to find the answer for x. So take a calculator and go 70,000 divided by 250. That makes 280. So along the x-axis, over at 280 is the x-intercept for that third statement. Now let's get the y-intercept by replacing x with 0. That means that 400 times y equals 70,000. Take a calculator and go 70,000 divided by 400. And that's 175. So this blue line is that third constraint. And a less than symbol means you want to shade underneath that. But I'm not going to do the shading yet, not until we pay attention to our fourth constraint. Again, this is standard form. We might as well leave it in this form and do intercepts method. When y is 0, x turns out to be 250. So approximately right there. When x is 0, the y is 250. So up here somewhere above the 175 would be where the 250 is. And then connect these brown dots together. Notice that they intersect each other right there. So our shaded in region is actually this shape in here. We know that we find the maximum of the objective quantity by using the x and y values from the vertices of the shaded in region. Well, this vertex is 0, 0. That would get us our minimum value. This one right here is 250, 0. This one right here is 0, 175. But what's this one where those lines intersect? Let's use our graphing calculator and the intersection feature of the calculator to find that ordered pair. For y1, I'm going to enter the blue constraint, but we'll have to rearrange that to get the letter y alone. So in parentheses, it will be 70,000 minus the 250x, close the parenthesis, and then divide by the 400. For y2, I'm going to do the fourth one, the one in brown ink. But again, we got to get the letter y alone by subtracting the x. So that will be 250 subtract x. I will also change my window settings so that it fits the drawing that I've done on paper. So for x minimum, I'm going to do 0. For x maximum, 280. For x scale, I'm going to count by 40s. For y minimum, 0. For y maximum, 250. And for y scale, I'm going to count by 50s. And then press graph. Here's the blue one. Here's the brown one. And we can see the intersection point. So second, calculate, choice 5, and then move the cursor on top of the intersection and press enter 3 times. And we're told that that intersection is at 200, 50. So now we know that that spot was 200, 50. Now we're ready to find our maximum profit. Let's use this ordered pair 0, 175. When substituting that into our objective quantity, we'll have 45 times 0 plus 50 times 175. And that's equal to $8,750. Next, let's use this ordered pair, the 200, 50. When substituting that into the objective quantity, we'll have 45 times 200 plus 50 times 50. That's $11,500. Finally, let's use this vertex of the shaded in region, the 250, 0. That will be 45 times 250 plus 50 times 0. That's $11,250. Now we can find our maximum value. It's $11,500 of profit, and Best Buy can make that profit if they sell 200 of the cheaper phone and 50 of the more expensive phone.